3.3 Rules for Differentiation, Part 2. Your objectives for this lesson are to apply rules for differentiation and to find second and higher order derivatives. We're going to start out with the quotient rule. So you saw the product rule in the last video. This is the quotient rule. At a point where v is not equal to 0, the quotient y equals u divided by v of two differentiable functions is differentiable, and d dx of u over v equals v du dx minus u dv dx over v squared. This seems tricky to remember, and it can be. It might help you if you wrote it like this instead, so there's just fewer letters around. So vu prime minus uv prime over v squared. You could also remember it like the derivative, so d is for derivative of high over low, so top number over the bottom number, so u is high, v is low, equals low, then derivative of high minus high derivative low, high over low squared. And I think it's helpful, the one on the bottom here, the one that's getting squared, is the one on the bottom over here. So that helps me to remember which one is on the bottom. Other than that, it's pretty similar to the product rule, other than you have a subtraction sign here instead of a multiplication, and addition sign from before. Okay. Example 1, differentiate f of x equals x squared minus 1 divided by x squared plus 1. So if this were your quotient rule, it is. You have u and v. Okay, so u equals x squared minus 1, v equals x squared plus 1. So we know f prime of x is going to be, we said, low, so x squared plus 1 times the derivative of the high one, so 2x, minus high times derivative of low over, so all over low squared. Okay, and now we just need to simplify. So I'm going to distribute my two x's, and we end up with 2x cubed plus 2x minus 2x cubed plus 2x over x squared plus 1 squared. These cancel, and I have 4x over x squared plus 1 squared. And I'm going to leave my answer just like this. Rule 7, the power rule for negative integer powers of x. So we saw positive before, here's the negative one that I told you about. So if n is a negative integer and x is not equal to 0, then d dx of x to the n is n times x to the n minus 1. Example 2. Find an equation for the line tangent to the curve y equals x squared plus 3 divided by 2x at the point 1, 2. So the first thing that we need to do is find dy dx. We need to do this because we need a slope for our tangent line. So this is dx of this. And I'm going to break this fraction up into two pieces so that I can simplify it a little bit. You see that the portion on the left here, I can subtract those exponents, cancel out an x. Just makes my math a little bit easier. Easy's always good. Okay. And I'm going to actually bring this up to the top. So I have my negative exponent. You can always change the side of the fraction bar that you're on by flipping the sign of the exponent. So this is x to the first. By changing it to a -1, I've brought it up to the top. Okay. So now we can get started. I'm going to take the derivative of the first term, and this is x to the first. When I bring down that exponent, I have 1 over 2 is still there, and I have x to the 0, which is 1. So I'm just going to leave that as a 1/2. Plus, let's bring this out in front, so -1 times 3, and then we have x to the -2 over 2. Okay, so this is 1/2 minus 3/2 x to the -2. And this is our derivative of the function. You could also write this as 1/2 minus 3 over 2x squared. Okay, and this would be the same thing. I'm just going to leave this like this for now, though. Okay, so now I know that we are at this point here, 1, 2. So I'm going to find the slope at that point specifically. So at x equals 1, slope is 1/2 minus 3/2 of 1 to the -2. 1 to any power is 1, which is, again, easy. So we have 1/2 minus 3/2 times 1, technically, don't need to write that part. So this is a -2 over 2, or a -1. So my slope at x equals 1 is a -1. Now the tangent line at 1, 2 with the slope of -1 is, well, I'm going to use y minus y1 equals mx minus x1. And let's see what we get. So y minus 2 is -1 x minus 1. Distribute this -1, so I get -x plus 1. And I'm going to add 2 to both sides to get y by itself. So y is negative x plus 3. And this is the equation of our tangent line at the point 1, 2. Last step, okay. So we've seen this before, we've been working with it. Y prime, remember this little dash is prime, is the same as dy dx. And this is the first derivative of y with respect to x. First, you might guess from that there are more derivatives after the first. Otherwise, it might just be called the derivative. And as it turns out, the first derivative may be differentiable. If you can differentiate something, that means it has a derivative. And the derivative of the first derivative is y double prime. So this is double prime. Okay, so dy prime dx, d dx, dy dx, d squared y dx squared. This is all the same thing, and it is the second derivative of y with respect to x. Okay, so the second derivative of y has 2 apostrophes instead of 1. You can just count them. And then, you may have snuck a peek of this before, the second derivative could also be differentiable. You could just keep going on like this forever, depending on how complicated your graph is. So if you differentiate the second derivative, if that's possible, you'll end up with this, which is y triple prime, okay, written also like this. So 3 tick marks, third derivative. Let's see that here. The third derivative of y with respect to x. I don't have anything else written there, but you could theoretically keep going forever and ever and ever. We're not going to see much past the third derivative, though, in this class at least. Okay. So this is your multiple prime notation. This is an n. It looks a little h-like, but it's an n. And this is y super n. That's how you would say that. And whenever you have the d dx, basically you knock that down by 1. So if you had 3 tick marks here, that would be 2 tick marks with this. So this is the nth derivative of y with respect to x. Again, whichever derivative you're using. So I think that's, yes, that is all for 3.3. And I will see you in 3.4.